Good morning. Today, my topic is regarding CMOS inverter and its fabrication process. Uh, we know what is the full form of CMOS. CMOS is a complementary metal oxide semiconductor where it is a device which is used to implement the logical functions. CMOS itself is an inverter, right? The work of an inverter is to when we give the input as in a zero, we will have the output as in a one. When we give the output has a input as in a one, so output we will have a zero. So in the further connections part, right? So we will use the two different types of transistors, right? CMOS inverter we will design with the FET transistors, right? Field effect transistors. One PMOS transistor is used and NMOS transistor is used. For the PMOS transistor, when the input is given as in a zero, right, the PMOS transistor will get on. When the for the NMOS transistor, when you view the input as in a one, the NMOS transistor will get on. Right, vice versa, right? When we have given the input as in a one to the PMOS transistor, so the PMOS transistor will be in the off state. So when we give the zero has an input to the NMOS transistor, so the output of the NMOS transistor will be the off state. So by using this logic, so we are designing the CMOS inverter right here. So we are using the two different types of transistors where we have the NMOS inverters, we have PMOS inverters, we have. For the NMOS inverters, only we will use the NMOS transistors, right? So we have the depletion mode of transistor and the enhancement mode of transistors. So in that, by using those two different types of transistors, we will design an NMOS inverter. So NMOS inverter is also gonna do the same, right? When we have given the input as in a zero, so we will have the output as in a one. When we have given the input as in a one, we will have the output as in a zero, right? So this is the CMOS inverters where the trend, right, in the market where we are using the CMOS inverters, right, to design any of the circuits. Where how the CMOS inverter is going to work, how the connections will be get connected, right? So the where when you see the diagram, schematic diagram or the symbol for the CMOS inverter, right? So first the PMOS transistor is connected to the VDD and the NMOS transistor is connected to the VSS. We have given a common interconnection between the gates, right, where the common input will be get given to that inverter. See, for example, like the common input have given to the both the transistors, right? So when you have given the zero or one, so both the transistors are has to work at the same time. So this is the priority where the both the if we have given the common input to the both the transistors, if the transistors is not working in a sim at the same time, so we have the problem to get the garbage values. So in order to avoid that, so the PMOS transistor and the NMOS transistors are connected together where the designing part, when we compare with the PMOS transistor and the NMOS transistors, the PMOS transistor sizes are 3 to 4 times greater than the NMOS transistor to avoid the delay between those two transistors. To avoid the garbage values right here, when you have connected or designed any of CMOS circuits, right, to avoid any of the garbage values or the delay between the circuits. So we will design the PMOS transistor is 3 times greater than the NMOS transistor. Why we have to design the PMOS transistor is 3 times greater than the NMOS transistor? See, for a, when we take the PMOS transistors, right? So in the PMOS transistors, so the majority carriers will be the holes. In the NMOS transistor, the majority carriers will be the electrons. So when we consider this, right, so the the flow, the momentum or the mobility of these holes is very less when you compare with the mobility of the electrons. So the electrons will move faster when you compare with the mobility of the holes. So in order to equalize the mobility of electrons and the holes, so we will design the PMOS transistor 3 times greater than the NMOS transistors. So these are the FET devices, field effect transistors. So when we have connected together, right, the gate terminal will be get used as an input terminals. So the FET transistors have the 3 terminals like gate, drain, and the source. So the gate and the drains, right, and the source are the 3 terminals where the gate terminal will be used to have the inputs, and the drain and the sources were connected to the VDD and the VSS. We can have the output from the terminals. So we can see the symbol representation schematic of your CMOS inverter. So where the A has given the common input to the PMOS and as well as NMOS. So when you have given the 0 as an input, the PMOS, right, connected to the VDD will be on, and NMOS connected to the V ground terminal will be get off, right? So the on and off has to occur in the same time where the output has to get the VDD, right? So where the PMOS transistor will drive the VDD output when PMOS transistor in the on state, right? When you have given the input has in a 0, the output at the Y, you will have the 1 has an output Y where the PMOS transistor is going to drive the VDD. So when the input A you have given as an A1, right, the NMOS transistor will be on. So when the NMOS transistor is in the on state, so it is connected to the ground terminal. So the output of the Y, right, it is driven to the ground terminal. So that how we will have the 0 and the 1 has an outputs. See, once again, we will repeat the time. When you have given the input has an a 0, this is a logic function of your CMOS inverter, how it will have the zeros and the ones at the output terminals. When you have given the input has an a 0, so the PMOS transistor will get on. So where it will drive the VDD to the output, right? So where how like we will have the 1 has an output. So when you have given the 1 has an input, the NMOS transistor will on, and what is the output you have? So it is gonna drive in to the ground terminal. So how you will have the 0? In that way, you will have the 0 and the 1 at its outputs. So how it is gonna work? So when you have given the 0 as an input, the PMOS transistor will drive the VDD where you will have the 1 has an output. You have given the 0, you have got the 1 has an output. When you have given the 1 has an input, NMOS transistor will get on. So what is the output you have at the capacitor at the output, right? So it is driven towards the ground. So where you will, it will make the output has an a 0. So in that way, you will have the zeros and the ones. See, right now, like we have to know like why we have to connect only the PMOS transistor to the VDD and the NMOS transistor to the VSS. See, when you have connected the huge transistors, right, where to have the inverter operation, right? So we have to connect the PMOS enhancement mode transistors. They both are the enhancement mode transistors where the PMOS transistor have to connect to the VDD and the NMOS transistor to be get connected to the VSS, that is ground. See, if we repulse the schematic diagram, if we are reversing that, right? So NMOS, if you have connected NMOS transistor to the VDD and the PMOS transistor to the VSS, the what is the inverter operation you require, it will not perform. And PMOS transistors where it has to drive the VDD, right? So by using the CMOS designing style, right? So we can design the number of circuit logics, right? So like, see, if you want to design in a NAND gate, right? So you can design the NAND gate by having the AND and structure of your PMOS transistor. Okay. So in MOS transistor also, we have to view the AND structure. See, for PMOS transistor, if both the PMOS transistors are connected in parallel, it will give the AND operation. For NMOS transistor, if the two NMOS transistors are connected in series, it will give the AND operation. If we have connected both together, right, it will give the NAND operation, right? So this is the thing, this is the formation of designings, right? So how the CMOS inverter will be used for different designings of the circuits. In the market, every circuits, right, every devices is built with CMOS design styles, right? Rather than to have the NMOS and the PMOS inverter designing styles. Okay. See, right here, this is a small description regarding the CMOS inverter. The CMOS inverters, right? How it is gonna be. These are the terminals, right? So representing, right, small complementary metal oxide semiconductor circuit, right? So this is the NFET and the PFET, right? NMOS are the PMOS, direct field effect transistor. Gates are connected together has an input, and the drains are connected together has an output. So NFET and the PFET sources are connected to the ground and VDD respectively, and NFET substrate is normally connected to the ground for all NFET devices in the circuit. Already we have discussed this, right? So how the connections will be done, right? So for the PMOS transistor is connected to the VDD, and NMOS terminals, the which is connected to the drain terminal is connected to the VDD, and the source terminal is connected to the ground terminals, right? The gate terminal we have given, we will give the input for the gate terminals, right? See how the operation will already we have discussed, right? So input voltage is down to 0 volts. NFET is off and the PFET is on, pulling V out to VDD. If V in is up, right, at VDD, NFET is on, hard, and PFET is off, pulling V out low to the ground, right? Already this is the thing we have discussed in the previous. The next, see, so how we will fabricate the CMOS inverters. See, for the fabrication process for the CMOS, so we have to get the all the two transistors has to be get fabricated. So all the two transistors is in the sense PMOS transistor and the NMOS transistor. So when you want to have the PMOS transistor and the NMOS transistor to be get fabricated together, so we have to use the methods like either P-well will be get used, or N-well, or twin tub, silicon on insulator process, and the triple N-well process. These are the methodologies we may use, right? So right now we will discuss the N-well process, how the N-well process is used for the fabrication of CMOS inverter. Okay. See, for this fabrication process, we have common 10 steps. For every time these 10 steps is going to be get repeated. Right here, first is the wafer fabrication process. Wafer fabrication process, what do you mean by the wafer? See, wafer fabrication is in the sense the base. What is the base we are using, right, for the fabrication process? So that is more important for us because we are using the silicon platform right here where the silicon materials are going to have is, so we are getting the silicon materials from the sand, right? So the silicon crystals we are collecting from the sand. So those crystals is heated, right, at the 1500 degrees centigrade to the 2000 degrees centigrade to have the liquid structure, right? So where that liquid structure is stored in the cylindrical format, so where we used to call it as a wafers, right? So that the sliced particles, we used to call it as a wafers, where we will make the platform. On that platform where we will have the IC designing, the circuit designings or the transistor designings will be get happen on that platform. right? The base, what is the base substrate? This is when you can see this, right? P substrate where you have collected, right? So your fabrication processes is processed on these P substrates. Okay. So the silicon dioxide is grown all over that. So why the silicon has to grow, silicon dioxide has to grow on the P substrate is in the sense. So the how it is gonna act as an insulator, right? So if any other materials, right? So you want to be get pour on the P substrate, right? It should not interact with the P substrate because these are the semiconductor devices. So these the semiconductor devices is in the sense where when you have taken any of the pure material and you have to impure that material with other materials, right? So if you have taken the trivalent element and you are impuring with the pentavalent elements, right? So where you are making it has a semiconductor devices. So these semiconductor devices is where we are regularly using for the designing parts. So the pure materials we can't use for this fabrication process, right? So the radioactivity nature of those materials may be the very high, right? So where it is not going to be get supported properly for the power dissipations and the power consumption parts. So we are using the semiconductor devices where we are getting the proper power analysis right there and the proper designing part in that formats, right? So the Fermi level energies is also in a better way, right? So when we are taking the semiconductor devices, see, so we have to form the semiconductor devices. So for that to form the semiconductor devices, so we are taking the pure material first and we are impuring it, right? So where the process is making to impure, and in that process we are making the transistors right there, right? So we are making the PMOS transistor on the same platform and the NMOS transistor in the same platform. See, for that purpose we have to pour the materials. First of all, silicon dioxide we are taking, where silicon dioxide is going to have the act as an insulator right here. So it is going to act as a barrier which protects portion of the wafer against the contamination of the substrates. Already we have discussed it is going to act as an insulator. So where this barriers protects the portion of the wafer against the contamination of the substrate. Silicon dioxide is laid out of by oxidation process done exposing the substrate to high quality oxygen and hydrogen in the oxidation chamber at approximately 1000 degrees centigrade. To form the silicon dioxide, we have the two different types of processes, wet oxidation process and the dry oxidation process, right? So for that purpose, we are using the oxygens is the dry oxidation process. Wet oxidation process is that we are taking from the H2O, that is from the water, we are heating it out and we are evaporated one we used to collect, and we are going to use that silicon as a silicon dioxide as a wafer, right, on the wafer, right? The surface is now covered with the photoresist, which is deposited on the wafer and spun to achieve an even distribution of the required thickness. Okay. See, photoresist, right, where it is permits to selective etching, right? Etching is nothing but we have to remove the part. Etching is nothing but we have to remove the particular area. If we want to remove the particular area right here, right? So this is the photoresist. After growing the photoresist is nothing but to increase the thickness of the device. That's it. So photoresist is nothing but we have to increase the thickness of the device. And in this process, the wafer is coating with the uniform film of photosensitive emulsions. Okay. See, if you want to mask the areas, we have to use the photolithography process. This we used to call it as a photolithography process, where we are using a cadmium rod. In from that cadmium rod, we are imposing the ultraviolet rays to have the masked areas, right? So to it is in the sense that so you are creating a particular area where your PMOS or the NMOS transistor has to be get it designed at that particular area. Okay, so for that purpose, your ultraviolet rays will be get used in that. So we will select the which area we need it on that particular silicon frames. Okay, see. So after creating, so this area, photoresist area, we can see, right, after imposing the ultraviolet rays, so we have etched and cleaned the area, right, without having any of the photoresist materials at that particular point. So we have removed that particular area, we have cleaned it to have our enwell process. Right now we are discussing the enwell process. This is the area we have created to have the enwell. Well is nothing but we knew that where the water as is water content will be get stored, right? That the well, right? So for that, so we have the huge P substrate right here. In that huge P substrate, we are digging a well, right? Some area we are going to dig in that P substrate. For that area, we will be used for to dump the N-type substrates. So see, listen carefully. We are using the P substrate, right? So we dig some area right there and we are dumping the N substrates right here. Okay. So where that well contains the N substrates in that. So by using that N substrate, we will design the PMOS transistors, right? In that N well, we will design the PMOS transistors, and by the PMOS substrates, we will design the NMOS transistors, right? P substrate and the N substrates. In the N well, we will have the PMOS transistors. In the P substrate, we will have the NMOS transistors, right? See, so the P substrate oxidation process, the wafer is immersed in the etching solutions of hydrofluoric acids, which removes the oxide from the area through which components are to be diffused. Right here, we will have to discuss one point. When you have created an N well, right? See, we have to create the three terminals for the PMOS transistor and three terminals for the NMOS transistor. So to design the PMOS transistor right here, so we have the three terminals, that is the gate, source, and the drain terminals. So here the gate is going to be get deposited by using the polysilicon material, and and PMOS source and the drains are going to be get diffused by using the N-type materials or P-type materials, right? So we have to understand the PMOS and the NMOS transistors has to be doped, right? So doping level will be done, right? So for the gate terminals, we will deposit the gate terminals. By using the polysilicon material, we will deposit the terms, right? So in the for the diffusion process will be done for the source and the drain terminals. So the etching wafer is immersed in the etching solutions of hydrofluoric acids, which removes the oxide from the area through which components are to be get diffused. Okay. So the next one, the removal of whole photoresist layers, right? So during the etching process, this portion of the silicon dioxide, which are protected by the photoresist layer, are not affected. The photoresist mask is now stripped off with a chemical solvent, hot H2SO4 materials. Okay. See, the thing is that when we are doping the terminals, right? So for the source, drain, and the gate terminals, the gate will be get deposited and the drain and the source are going to be get diffused. See, right here in this step, we are diffusing the N well in the P substrate. So we are diffusing the N well, right? So we are creating an N well where we have to form the P-type substrates. So, well, sorry, we have to form the PMOS transistors, right? On the P substrates, so we have to form the N transistors, NMOS transistors, right? In the N well, we will have the PMOS transistors, and for the P substrates, we will have the NMOS transistors. See, in that P substrate, the layer silicon dioxide is now removed, and by using hydrofluoric acid, then after we are depositing the polysilicon gate oxide right here. We are depositing the polysilicon gate oxide. So where the gate terminal is deposited right here, and the source and the drain terminals are diffused. Okay. So after diffusing, where we needed the gate terminal, right? All the in from top to bottom, right? So sorry, from the left to right, we are not going to use the complete polysilicon. So we wanted to have the particular area where the gate terminal is required, right? So the remaining area has to be get etched out, right? It has to be get removed. So for the once again, the ultraviolet traces will be used for the etching process, the all the oxide layer, then after polysilicon layer, after that, the all the area will be get removed by using the ultraviolet traces, right? So after that, so this is the gate terminal has been got formed. Then after, once again, we have to get the drain and source terminals, right? For that purpose, the same process is going to be get repeated. So once again, you have to layer the oxide layer. Then after you have to photoresist layer. Then after you have to impose the maskable area, like by using the cadmium rods. You have to dig the area of it for the source and drain terminals. Then after you have to diffuse the N and the P-type materials into that source and drain terminals. Right here, the source and drains are terminals are equally doped. Right, when you see in the BJT, the emitter, collector, and the base terminals, collector and the emitter base terminals, right? They are moderately, highly, and lightly doped, right? Those three terminals. Right here, the source and the drains are equally doped. Okay. So the gate terminal will be deposited, source and drain terminals are equally diffused, right? The doping process will happen, right? The oxide layer we will have, and the diffusion, metallization for the metallization process, make masking and diffusion, right? Regions for diffusion of N-type impurities. Using masking process, small gaps are made to have the source and drain diffusions. Okay, see, right in this step, right? So we have at the one time, we have diffused the N-type substrates, right? So the N-type terminals has been got diffused, right? In the N well, we have the N process, right? So N material has been got diffused. In the P-type substrates, we have the source and drain terminals of N diffusion. Okay. So where the P, this is the NMOS transistor. The source and drain terminals is with the NMOS substrate. So we used to call it as an NMOS transistor. If the source and drain terminals are with the PMOS, right, material, P-type material, we used to call it as an PMOS transistors. Okay. So the oxide layer is stripped out, right, where the next P-type substrate is going to be get diffused in the next one level. See, so in the next level, we have the P-type substrate has been got diffused, right? So has been created, dig that particular area, and they have diffused the P-type substrate in this process, right? See, so thick field oxide before forming the metals terminals are thick field oxide is laid out to form the protective layer for the region for the wafer, which no terminals are required right here, right? So then after metallization process, right? So the metallization process for the interaction of the one transistor or the one terminal with the and next any other terminals. Formation of the terminals will be get happen. Gaps form after removal of excess metal terminals for the interconnection parts, right? See, so after creating the terminals, we have see already in the first I have said we are going to be get use the common steps, right? So the first one is the wafer fabrication, second one is the oxidation, third one is the photolithography process, fourth one is the deposition, fifth one is the ion implantation, sixth one is the diffusion, seventh one is the metallization process, right? So annealing, passivation, right? So packaging part where it is comes under when this processes is happening, the overheat is going to be get happens, right? The cooling down the devices is those processes will be get happens, right? See, it is common steps, right? So every time we will move with the oxidation process, right? Photolithography process, right? Removing the areas, etching the areas, and creating the source and drain terminals and diffusing the in diffusion or the P diffusion for these terminals, right? So this is the fabrication steps, right? So where we will use for the CMOS inverter fabrication. This is the end-well process. End-well process which is used to design the CMOS fabrication, right? So thank you for this opportunity. Let me meet in the next class.